We're going to do kind of an abbreviated version of Chapter 9 because you'll find that there's really not any new principles that we haven't learned in here. It's about how to apply our principles about forces and torques to situations where an object is sitting in equilibrium. And for us, we're going to think of, at least all the problems we'll do, we would say something's in equilibrium if it is not moving at all. That means it's not rotating and it's not moving by translating through space at all. Okay, and we want to find the conditions on the forces being applied to it so that the object would be in equilibrium. And that probably seems pretty straightforward. We already know a lot about what has to be true from Newton's second law. If the sum of the forces equals ma, and A has to be 0, in other words, if the object's in equilibrium, it means it's not moving, then certainly the acceleration of the object is 0, and therefore the sum of the forces on it has to be 0. So I'm going to build up a list of the sufficient conditions that have to be met for an object to be in equilibrium, to not be moving in any way. So the sum of the forces has to be equal to 0. That's a vector equation, which really means in terms of x, y, and z components, there are 3 separate equations we could write down if we really have an inherently three-dimensional problem. Now, that seems like it might be enough if you don't think too carefully, but if you think a little bit more deeply, for example, we imagine this rod sitting out in outer space. We apply a force in this direction and an equal and opposite force at a different side of the rod in the downward direction. We're in outer space, so there isn't any gravitational forces, but in that case, the object is not going to be in equilibrium. It's going to start rotating. And so clearly this is a case where the sum of the forces being applied to it are summed to 0 because the two forces cancel out. So that's not enough. We need to add another condition. And because when forces cause things to rotate, that means there's a non-zero torque being applied to it. It's not too hard to imagine that the second condition that has to be true for an object, an extended rigid body, to be in equilibrium is that the sum of the torques on it has to be 0. The only thing that's a little bit tricky relative to what we've done before is that before, in a lot of cases, we had a fixed axis, or, sometimes we did a wheel rolling down a road, but at least it was clear that it was sort of, from the point of view of someone in the car, it was rotating about the center of the wheel. Here, this thing's sitting in outer space, and it's not exactly clear that it's going to rotate around a fixed axis or anything like that. So the statement is that the sum of the torques has to be 0 about any rotation axis. And at least at first that might sound like a bit of a nightmare because we don't want to have to check that the torques sum to 0 about every rotation axis, but one can show that if you just sum torques about any rotation axis at all, if it's true that the sum of the torques equals 0 for that axis that you used, it's also true that if 1 and 2 are true for that one axis you chose, then they will also be true had you chosen any other axis. So you can be a little bit creative about choosing the axes about which you sum torques. All right, let's try an example problem. I've repeated the conditions: sum of the forces equals 0, sum of the torques equal to 0 for an extended object to be in equilibrium. Here our object is going to be a seesaw, the board, which is the seesaw, and we've got 2 kids sitting on the seesaw. The seesaw itself has a mass of 40 kilograms, and of course the seesaw's center of mass is at the center, so we can pretend that the 40 kilogram times 9.8 force is being applied in the downward direction right at the center of the seesaw. So the kid on the left has a mass of 30 kilograms and is 2.5 meters from the pivot, and the kid on the right has a mass of 25 kilograms and sits some distance that we want to find out from the center so that it's exactly balanced. They can balance it without touching the ground. So there are 2 questions in this problem. The first is, when the seesaw is balanced, what force does this pivot have to exert upward on the seesaw? And the second is, if the child on the right has a mass of 25 kilograms, how far should she sit? In other words, what is that x in the diagram so that the seesaw will be balanced? If she sits too far outward, the seesaw will go down on her side. And if she sits too far inward, the boy's side will go down. Okay, so we're just going to apply the sum of the forces equal to 0 and the sum of the torques equal to 0. So let's first apply the sum of the forces equal to 0. I'm saying F net y equals 0. Right now I don't have a set of axes on here, but I'm going to take plus y to be up. And so these two children will be exerting downward forces on the seesaw. The weight force will be a downward force on the seesaw, and the pivot point will be an upward force on the seesaw board. Okay, so let's add all those together. The pivot comes in with a plus sign because it's pushing up. I'm going to call plus y upward. And then all the other three forces, the force from the left child, the right child, and the seesaw's weight itself, all come in with negative signs. And so when we add those to 0, we can solve for the force that the pivot must exert upward on the seesaw, 931 newtons. B, if the child on the right has mass 25 kilograms, how far should she sit out on the right? And in this case, we've already done the sum of the forces equals 0, and we haven't figured out anything about what x is. So our only tool we have left is the sum of the torques equal to 0. And in this case, we do have kind of a predefined or obvious rotation point. So I'm going to sum torques about this pivot axis. We'll see in later problems that's not always going to be so obvious what to use. But for now, let's sum torques about point P. Okay, and I have to make some convention for what torques are going to be positive. I'm not sure which ones I took in the solution, but let's assume I took counterclockwise to be the positive rotation direction when I'm summing torques. Let's see if that's true. Yes, the 30 kilogram times 9.8 force has a moment arm of 2.5 meters. That's this torque over here. And we're putting it in with a plus sign because it's trying to turn it in this counterclockwise direction. So it looks like I've chosen counterclockwise to be positive. Somehow that might have been drawn over here and it somehow didn't make it into the scan or something like that. But I should specify which direction is the positive rotation direction. Okay, so this one comes in with a plus sign, and then the girl is exerting a negative torque about point P, and so that's because her weight force is trying to rotate it in the clockwise direction, which I'm calling negative. So that's her weight, 25 times 9.8 times the moment arm, which is x in this case, and it's the x I want to find out. There are two other forces on the seesaw. The pivot force upward is being applied right here, so its moment arm is 0. That's why I didn't have to include it in there. And the seesaw's weight force is downward, and again we can pretend that it is located at point P or being applied at point P because that was one of our shortcuts that we learned about calculating torques. So again, its moment arm will be 0. So there's just two other zeros added onto there that I didn't show. So I get a nice simple equation when I say the sum of those has to be 0. I can solve for x. X has to be 3 meters. All right, here's a voting question related to this idea of something being in equilibrium. A 1 kilogram rock is suspended by a massless string from one end of a 1 meter measuring stick. Okay, so here's a meter stick. Here's a 1 kilogram rock attached to a string. And what is the mass of the measuring stick itself? In other words, this rod here, if it is balanced by a support force 0.25 meters from the end. In other words, the configuration that's being shown here is balanced. What does the mass of the meter stick have to be? If the mass of the meter stick is too big, it's going to fall, it's going to start rotating in this direction. If the mass of the meter stick is not big enough, the rock's going to win and it's going to start rotating in this direction. If the mass of the meter stick is just right, it will neither rotate one way or the other. The answer here is 1 kilogram, and that's because in calculate we only have 2 torques. Well, I guess there are really 3 torques about this pivot point that are being applied to the meter stick. There's the downward force from the rock. That's just mg being applied in the downward direction. There's the pivot force upward, and then there is the gravitational force on the entire rod, which we know we can pretend is located at the center of mass or is being applied there. And so if we have 1 kilogram times 9.8 going down there, we're going to need 1 kilogram times 9.8 being applied at the center of mass, because this is a symmetric object. Its center of mass is always at the center of symmetry, and that's at the half-meter mark of this particular object. So we need 1 kilogram times 9.8 going down there to balance out this one, and that would make it perfectly balanced so that there is 0 net torque. So we need the same weight for this meter stick as there is for the rock there. All right, second problem, we're going to see things get a little bit more complicated in this case, or at least less familiar. Here is a diver of weight 500 newtons, that's m times g they're giving us there, standing motionless on the end of a diving board. We're going to pretend this diving board is very stiff so it doesn't bend at all, 4.48 meters from the left end. And the diving board itself has a mass of 142 newtons. The board is attached by 2 pedestals, A and B, shown there. A is the left one, B is the right one. They're 1.55 meters apart. Find the force exerted by the pedestals A and B by the board. For each, specify if the force is upward or downward. Okay, so both of these pedestals have to be either pushing or pulling on the board, and you may have some intuition about it. In other words, if A weren't there, this thing would start rotating in this direction, right? And if B weren't there, the whole thing would start rotating around in this direction. So it seems like we need non-zero forces for both of them. We'll find out from the algebra what the directions are. All right, so we're going to take some conventions. Because I'm going to take plus y to be upward, and let's, just for the sake of doing the algebra, let's assume the force of A on the diving board is in the upward direction, and the force of B on the diving board is in the upward direction. We don't know that ahead of time, or you may not have that intuition, but what we can do is put those in and assume those are correct, and when we do the algebra, if we get a negative answer for B, for FB or FA, then we'll know that we chose exactly wrong, and that one was actually a downward force in that case. Okay, I've also marked out the weight of the diving board. It's located at the center of mass of the board, halfway outward from the left end, and then the additional force downward from the diver, which is equal to the weight of the diver. And so we've got to, I've taken counterclockwise to be the positive torque direction, and I'm going to sum torques about point A. You don't have to do that, but we'll find out here there are good and bad choices for it. But let's first start off with the easy cases. All the forces are acting in the y direction, so we don't need to do F net x equals 0, but here F net y equals 0, where plus y is up. We get FA and FB, if we're assuming they're in the upward direction, they come in with plus signs, and the 142 and the 500 come in with minus signs. All those have to add to 0, and that doesn't get us to anything that directly tells us an answer. We're just going to hold on to that equation that says FA plus FB is 642 newtons. Now let's sum torques about point A, and just take it on faith that that's a good thing to do right now. Some of the torques about A. Well, let's see. The diver's weight is trying to rotate in the in the clockwise direction, which is the negative direction. So that's going to come in with a minus sign. Same thing with respect to A for the weight of the diving board. So that's going to come in with a minus sign. That's why these two terms have minus signs. Whereas B is pushing upward on the board, or at least we're assuming it is right now. So it would come in with a plus sign because it's trying to turn it in the counterclockwise direction. I'm calling that positive in this assumption. Okay, so we just got force of B times its moment arm, 1.55 meters. The force of the weight of the diving board, 142 newtons, times 2.24 meters, that's half the length of the diving board, is its moment arm, and 500 newtons times the full length of the diving board, and both of those last two come in with minus signs because of my choice of positive directions. Add them all, and you get 0 if it's in equilibrium. Okay, That tells us this only involves FB. And so I can solve for what FB is. FB is 1,650 newtons. And notice it didn't come in with a minus sign when I did the algebra. So that means FB is upward because I got a plus sign for my answer. And now to finish up, I can plug that in up here and solve for FA. And when you do that, you'll find out FA is negative. FA is minus 1,008 newtons. So that means even though I assumed without knowing that FA was upward here, we actually need a negative or downward direction for the force FA. And I'm seeing that from the minus sign there. And you can imagine that, right? If A were not pulling downward, the whole thing would sort of start rotating around B, right? So in the clockwise direction. So A has got to be pulling down to keep it from rotating in the clockwise direction about B. Now, why did I choose point A to sum torques about in this case? Well, one reason it's a good thing to do is because one of the forces that's an unknown, one of my variables, one of the unknown forces, is being applied at position A. And when I do that, FA won't come into the torque equation because its moment arm is 0. So whenever you sum torques about a point, if you have a choice of where to sum torques about, it's always good to sum torques about a point at which one of your unknown forces is acting. So A was a good point. B would have been just as good. You know, if I had sum torques about B, I would have found out FA from doing the net torque about B is equal to 0. And then I could have plugged up here and solved for FB. Either one's good. But I wouldn't want to sum around here or around here. Why? Because then I would have an equation that involves two variables here and an equation that involves two variables down here, and I'd have to do a little bit more algebra to do it. So it's always nice to just directly get one of your variables from one of the equations without having to substitute. So that's how we kind of choose sometimes. All right, maybe we'll take a little break here and I'll let you try your hand at problem 3. This is something attached to the side of the building. We've got a 2-meter long beam here. It's got a mass of 300 kilograms and it's attached to the wall via a pivot here. Okay, so this beam is free to rotate around that pivot while it's attached to the wall. The pivot doesn't have any friction in it. If there were nothing else in this problem, the beam would just fall down and slap the wall. So we've got to have a cable attached to the wall. So we attached a cable to one end and attached it to the wall, making an angle of 25 degrees with the horizontal, and that holds the beam in place. There's also a lantern or light that's hung from the end, and that has a mass of 100 kilograms. Okay, so all of this is happening and the object's in equilibrium. The object in this case, I'm thinking of my object as being the beam, and a bunch of forces are being applied to it, and it's in equilibrium. Find the tension in the cable and the horizontal and vertical force components that the hinge exerts on the beam's left end. So in this case, there's clearly got to be a tension in this cable. We're supposed to find that. But there's got to be, well, first of all, there's got to be a horizontal force component by the pivot on the beam. If there weren't, the beam would just go into the wall, right? The wall has to be pushing outward on it. Otherwise, the beam would just get pushed into the wall by by virtue of the tension pulling there. And there's got to be an upward force component from the pivot. In other words, if this pin weren't pushing upward on the left end of the beam, then the whole beam would just start sliding down the wall and fall downward too. So there's got to be both a horizontal and a vertical force component there. So you can call those your unknowns, maybe an Fx and an Fy for the force of the pivot on the beam. And then we've got an unknown T there. See if you can write the sum of the force X components equals 0, sum of the force Y components equals 0, sum of the torques equals 0, and figure out what those three unknowns are. And we'll be back with the solution.